Tem VGA.
Okay.
Well, next speaker, Eduardo Granado.
Talvez não seja. Ele está no HDMI ainda, então tem que passar para VGA.
Tá vendo? A HDMI está aqui, você está vendo VGA em algum ponto?
Talvez.
Isso, é porque ele está com o conversor para converter para HDMI.
Então tem que usar a entrada de HDMI. Essa entrada aqui?
Tenta usar essa, acho que essa deveria funcionar com esse VGA. Quando o mínimo do TI chegou, porque antigamente o VGA funcionava nesse computador aqui. Só que
Vou tirar.
para de usar.
Vou tirar para você. Opa, deixa eu uma coisa aqui.
Não entendi tudo.
Okay.
Eduardo from University.
So, first of all, let me thank the organizers for the invitation. I'm very pleased to be here to show some of our experimental results on the electronic nematic order and fluctuations in the iron pnictides. I'm going to show basically Raman scattering mostly and some synchrotron X-ray diffraction data. So our group is mostly from the University of Campinas, UNICAMP. And the results that I'm going to show you are mostly the PhD thesis, part of the PhD thesis of my student Ulisses Caneco. And the group is also completed by Mário Piva, Paulo Gomes from Unicamp, and Gaston Barberis, Pascoal Pagliuso, and myself. From Universidade Federal do ABC, you have Ali Garcia Flores. And from Ames Lab, we have Jay Yan, Lograsso, and David Vakning. So it's a collaboration of three different groups. Let me start making a general introduction about these systems here. The iron-based superconductors. So originally, superconductivity in these systems were discovered in the fluorine-doped lanthanum, oxygen, iron, arsenic, with Tc equal to 28 Kelvin. And the crystal structure of these materials can be seen as composed of layers of iron arsenic, where each iron is surrounded by a tetrahedron of arsenics and making like a layer. And these layers are sandwiched between rare earth layers and also oxygen layers, where the fluorine can be doped into. So as I mentioned, superconductivity was originally found at 28 Kelvin, and later on in the gadolinium, iron, arsenic, oxygen doped with thorium, they got the maximum Tc in this bulk system of about 56 Kelvin for doping of 20% of thorium. It's interesting to note the following: when you don't have any kind of doping at all, the iron layers they order antiferromagnetically. They have like a stripe antiferromagnetic order that I can draw in here. So we have in one of that direction, the nearest neighbors they order ferromagnetically, where in the opposite direction, the nearest neighbor they order antiferromagnetically. And that's interesting because the structure itself is tetragonal at high temperatures. So when at low temperatures we have a distortion in the lattice. So here you see in blue, you see the tetragonal unit cell in the AB plane, and at low temperatures you have an orthorhombic distortion, and so you have like this green a square rectangular lattice, which is defines an orthorhombic structure with 4 iron per unit cell at low temperatures, while at the tetragonal structure has 2 iron, half the volume, and 2 ions per unit cell. So for the undoped compound, we have this this magnetic structure, and if you measure resistivity, you get something like this black curve here. You have like a peak or a maximum in the resistivity at a temperature nearby 140 Kelvin, and below this temperature the resistivity drops, and this temperature corresponds to the magnetic ordering temperature of these iron layers. And for the undoped compound, for this family at least, there is no superconductivity, while for the thorium doped, what happens is that this maximum temperature of resistivity corresponding to the magnetic ordering, it goes down in temperature, and finally disappears as the superconductivity shows up in these materials. So this is pretty much what happens. You have doping, you reduce the magnetic ordering temperature, at some temperature you have the superconductivity coming up. That is not the only system where superconductivity has been found in the iron materials. For instance, the iron selenium, which only has this tetrahedral network with iron, but instead of arsenic you have selenium, and no intervening planes of other elements. You just have a stacking of iron selenium, and the iron selenium system, there might be fine superconductivity too, and most interestingly, the superconductivity can go to very high temperatures at certain special conditions, for instance applied pressure, and in this particular case where maximum transition temperature was found, we can potentialize superconductivity by strain, and then in this case you have a single layer of iron selenium deposited over a strontium titanite substrate doped with niobium, and for this case you have just the right strain in the plane, in the layer, to optimize the TC, and in this case the TC goes up to above 100 Kelvin. So that's pretty much, as far as I know, the maximum TC that has been found in this type of materials, and that's comparable to the cuprates. So it's a very strong TC. A very interesting aspect of the system also is what we call nematicity, and it is found originally. It's below the magnetic ordering temperature. Normally you have this. Sometimes you have this. Mostly you have this orthorhombic distortion, and that, however, you have like domains, orthorhombic domains, which are randomly oriented in a single crystal with equal occupancy of domains. So in principle, you have like isotropic conductivity in the tetragonal plane above at high temperatures, but you still have isotropic conductivity below the magnetic ordering temperature, because you have this equal population of domains. However, you can detwin the sample. You can increase the population of specific domain in expense of the order by applying strain. And when that's done, the resistivity curve can be measured, along the domain, the strain direction, or perpendicular to the strain direction. And for relatively small strains, it is found that the resistivity for measured along the strain and perpendicular to the strain are quite different. They can be quite different, and that depends on doping. So for like 0% doping, just the pure material, you already have some difference in the conductivity. When doping starts, you start to see more pronounced the difference between the resistivity or the conductivity in both directions. And when superconductivity shows up, again, the system becomes isotropic, but you can note that for some intermediate doping, regime, the difference between the resistivity can be quite large, a factor of 2. And that's very impressive because the orthorhombic distortion itself is a very small and very slight orthorhombic distortion. It's about a 0.3% difference between the A and B lattice parameters. And in principle, it should not be expected, since you already have a metal, it should not be expected to have such large differences between resistivity measures along these directions. So it was inferred that there is like an electronic order that is somehow responsible for this highly anisotropic resistivity in these materials. And then a phase diagram was actually drawn. I hope you can see that here, where here you have the electron doping and here temperature, and at low doping and low temperature, you have basically the orthorhombic and with phase with stripe magnetism. And then here you have for zero doping, you have this transition where that is both a structural transition and a magnetic transition, where the system become tetragonal and non-magnetic. For doping different from for electron doping, for some electron doping, we start realizing that the transition temperatures for the magnetism, for the magnetic transition temperature, and the orthorhombic transition temperature are not the same, exactly the same. So they are slightly different. So and then here in red, you have a regime where the magnetism has already disappeared, but the structure is still orthorhombic. And then at a slightly higher temperature, the system becomes also tetragonal again. And this difference between the magnetic transition temperature and the structural transition temperature starts to increase as the doping increases. So this regime is called the nematic regime, where the magnetism is isotropic, but the structure and also the electronic conduction is still anisotropic. And it's realized later that above this nematic phase there are still some sort of fluctuations that can be observed by Raman scattering, which I'm going to show you later. And this is, it's a very interesting regime where you have this kind of mysterious electronic fluctuations that permeates the response of the system. And for sufficiently high doping, you see the superconductivity dome over here, which resembles somewhat the phase diagram of the cuprates. So this system has attracted a lot of interest because one of the reasons that some people think that we can understand better the cuprates if you proceed in the research of this system. So the standard scenario to understand, not to understand, but to describe what's going on here is that at sufficiently high temperature, you have like a tetragonal phase with no magnetism and no anisotropic conduction. But on cooling, we start having what we call the anisotropic magnetic fluctuations, like the phases, the magnetism is already trying to set up. And with that, since the magnetism is a stripe magnetism, these kind of magnetic fluctuations, they induce some kind of orbital fluctuations, some kind of differentiation, at least locally, some kind of differentiation between the XZ and YZ orbital occupations, because that kind of selects some preferred direction to have the magnetic coupling more satisfied, and that's also connected with some fluctuations, some orbital differentiation in the iron orbitals. And connected with that, you have like orthorhombic fluctuations going on too. So you have all these coupled magnetic bar, electronic bar structural fluctuations that are interrelated. And one of the important questions is, who is driving that? Who is the driver's seat, as people say? And then on cooling, we have some. Finally, we have some transition which coincides with the orthorhombic, the structural phase transition, where we finally have a long-range orbital disproportionation that we call this nematic phase. And sometimes in different temperatures on further cooling, we have this stripe SDW, spin density wave magnetic phase in this system. So that's the standard scenario to describe the system, where the electronic and the structural transitions are the same, and the magnetic transition may be in a different temperature depending on doping. So just to finalize this slide here, you know, two important questions about this description is, again, as I said, who is driving this, the magnetism, the charge fluctuations, or the lattice fluctuations? And the second question is, what's the relation of these nematic fluctuations with superconductivity in the system? Can they help, or do they compete with magnetism in this system? That's kind of the issues that are being discussed nowadays on this iron pnictide physics. And then I come to Raman scattering, which is actually the main technique that I'm going to show here. It's been shown by several works that Raman scattering is actually sensitive to nematic fluctuation. So we have inelastic light scattering that can lose or gain energy when interacting with these fluctuations, which can, as I mentioned, could be you know, charge fluctuations or spin fluctuations. They are coupled together. And actually, there are mechanisms that have been proposed to explain the Raman signal, either considering they come from the charge or orbital nematic fluctuations, or if they come from spin nematic fluctuations. As I mentioned, both of them are there. And the question is, which are giving the Raman signal? And there are actually, you know, several groups, making arguments for charge fluctuations as a Raman, as the generator of the Raman signal, and some groups are making the case for the spin fluctuations, spin nematic fluctuations, as the generator of the Raman signal. This signal here, as you see, it has a maximum at a temperature like 140 Kelvin, which is very close to the magnetic ordering temperature in this system, and also, of course, with the structural transition temperature here. And then it goes up to this temperature, then goes down below. It has the right symmetry. It is B2G symmetry for the tetragonal unit cell. It has the right symmetry in both mechanisms to be associated with the nematic fluctuations. And then comes our the motivation for our work. So when we started working on that, we saw that the nematic fluctuations were already extensively studied by Raman scattering, both in the barium arsenic 2, iron 2 arsenic 2, they called so-called 1-2-2 systems, either pure or lightly doped, where the TAF, the temperature of the antiferromagnetic stripe ordering, is very close to the orthorhombic transition temperature. They may separated by 1 or just a few Kelvin. And also this system has been studied by Raman scattering at iron selenium at ambient pressure, where only the structural transition temperature is present, but no static long-range order, magnetic order is there. So we note that there is no systematic electronic Raman scattering investigation for materials where we have both the magnetic and the structural transition temperatures that are well separated by, you know, more than a few degrees. And we think that that's an important case, because in this case there are potentially more disorder, and then this disorder can actually give us insight on what's going on here, up to a point, of course. So these are our samples. We studied this lanthanum, iron, arsenic, oxygen. This is undoped, the original, the grandparent iron pnictide that was discovered first. Then it was abandoned by most of the scientific community because it was difficult to grow, much more difficult than the 1-2-2 system. But still, we have good samples of these, and we have this sample that shows that you know, you have like a magnetic reflection, Bragg reflection by neutron scattering that shows that the magnetic ordering temperature is about 140 Kelvin. And then you have the separation of the Bragg peaks, the structural separation of the Bragg peaks that goes to 0 at a temperature that does not coincide with the magnetic ordering temperature. It's about more than 15 Kelvin of difference. So this is 140 Kelvin, 145, 54 Kelvin. They are pretty much splitted. And another sample that we studied, we studied this one, and also wanted to study a material belonging to the 1-2-2 family, which as I mentioned to you, it was more studied, but we have a stronger doping here so that we could identify, in this case, 3 transition temperatures. Like this is a resistivity curve. You have a first transition at 20 Kelvin, which is the superconductivity transition temperature, and then resistivity also shows this characteristic peak in the resistivity at the magnetic ordering temperature, and then there is another feature which is marking the structural transition temperature. We can see that more clearly in the derivative of the resistivity. You have clearly the 2 peaks, 2 negative peaks, marking the 2 different transition temperatures. You also have in the specific heat, you have the 2 transitions showing up. So there are clearly 2 separate transitions in these samples. And in this case, the difference between the 2 are 20 Kelvin. So X, the doping here, was determined by EDS spectroscopy, energy dispersive spectroscopy, which is 24% doping. And this is what we have here. We have, this is the spectrum, the electronic Raman scattering here for the 1111 sample, the undoped 1111. So at high temperatures, you have basically noise. You may see something over here if you're, optimistic. But when you cool down the material, you start to see that the broad electronic Raman scattering starts to develop a specific structure, which can be, deconvoluted as a sum of this blue dashed blue peak here, which turns out to be omega times a Lorentzian curve, and then this purple curve here, this purple component is related with some 2 magnum Raman scattering that peaks a very high frequencies, which cannot be seen in this scale, but doesn't interest us very much. What interested us is this dotted blue curve here, which starts developing as we cool down. And see 163 just above the orthorhombic transition temperature. You have already have a very well pronounced signal. 143 again have a very pronounced signal. And then we cool down again below both the magnetic and the structural transition temperatures. This signal disappears. So you divide that by omega. You divide that the Raman the intensity by the Raman shift, and then you have this peaked these curves which are peaked at 0 frequency, and you can fit very well with Lorentzian curves. So that's very characteristic of what you call a quasi-elastic peak, essentially a Lorentzian center at 0. And then we are measuring not the peak, but the side of the Lorentzian by Raman scattering. That's a very, very, very well accepted feature characteristic of the nematic fluctuation signal by Raman scattering. So we can fit this signal here, right, with a Lorentzian, and from that we get the area and the width as a function of temperature. And that's what we have. We plot the area of that nematic peak as a function of temperature, and then you also have the width of that peak as a function of temperature. So you see that, interestingly, the area, and from the area and the width, of course, you have the height, which is the area divided by the width. And you see that both the area and the height, they keep, the signal goes up, and still, this first temperature at 155 is the orthorhombic transition temperature, and the second one is the magnetic transition temperature. And that in green, you have the nematic phase. And you see that the signal keeps going up in the nematic phase up to temperatures which are very close to the magnetic ordering temperature, which is surprising in a sense, because it has always been accepted that the nematic transition temperature coincides with the orthorhombic phase transition, not not necessarily with the magnetic phase transition. And at least for this sample, we have, we are seeing like critical fluctuations that keeps going up after the transition, which was thought to be the critical temperature for these fluctuations. So that's unexpected. And also unexpected is the fact that, you have this width that goes down. Goes down, meaning that you have fluctuations which are less dynamic, getting slower as you cool down. And then you see that at the the structural transition temperature, these fluctuations experience not a freezing, but it gets cooler. It gets more. It gets slower. Let's say that. And so the surprising observation here is that this structural transition is not apparently doesn't appear to be the critical temperature for the nematic fluctuations that we're seeing by Raman scattering, but these nematic fluctuations are still seeing the orthorhombic transition. I mean, they get slower when you get into the orthorhombic phase. And we also studied, again, as I said, the 1 to 2 system, okay? And then this system was, this sample we have to characterize it better because it was not previously studied. So we did it, the synchrotron X-ray diffraction. Here, I'm not going to get into too many details, but at high temperatures, we have this 220 reflection, which is supposed to be a single reflection. So that's what we see at high temperatures. And when you cool to the orthorhombic phase, the 220, because of the rotation of the lattice of the unit cell, it becomes 4020 and 0420. It becomes two reflections that we see both of them because of the twinning. We didn't detwin the sample, so we're supposed to see two reflections. And at low temperatures, you see this thing that is not clearly splitting, but you see something that changes, right? You have one reflection, and then you have some broad feature that apparently is actually the two orthorhombic reflections that which are overlapped. And this overlapping happens because it's not so clear the orthorhombic distortion here because with this doping, cobalt doping, you can't be completely homogeneous. There are some fluctuations in the doping, and that changes a little bit the lattice parameters of parts of the sample. So we have the broadening of the Bragg peaks not only in the orthorhombic phase but also in the tetragonal phase. So it's more difficult to study in detail the structure for this kind of doped systems, but we clearly see that there is a transition going on here. But you see that you have in the magnetic phase transition, you have something going on, something changing, but things kept changing between TAF and TO. So we can still identify this 152 Kelvin as the temperature where start having this orthorhombic domains, and the TAF is the temperature where the structure stops to evolve. And when you do Raman scattering, we basically reproduce the same results that we got for the 1111 system. We have this quasi-elastic peak, this nematic fluctuation peak, which area keeps going up on cooling up to temperatures close to the magnetic ordering temperatures. And we also see some anomalies in the width of this peak related to the structural phase transition. So again, we don't see the peak at the structural phase transition. We see the peak at close to the magnetic phase transition, which is also surprising, but apparently consistent with the other material that we have studied. When you compare that to well-studied, well-characterized samples of 122 without doping, we see that the nematic fluctuations are moving to the higher frequency side, so they are faster. 5? Okay, I had 5 minutes before, but great. So this undoped system, it does show nematic fluctuations, but they are quicker, they're faster than the samples that we studied. And then, so the question is, what's going on? I mean, nematic fluctuations apparently are slower for the samples that we studied, which shows a separation between the two temperatures. And apparently what's going on is that when the nematic fluctuations get lower, it gets to the scale of the phonons. Right? When these electronic fluctuations get into the time scale of the phonons, the crystal lattice gets more responsive to the electronic fluctuations. And we believe that this factor is making the orthorhombic phase transition, the magnetic phase transition gets separating more because of these lower electronic fluctuations, which are pushing the lattice fluctuations with them. So that's pretty much what we conclude here. And you know, something that we don't understand yet, but it's a very interesting result, that this cap, the quasi-elastic peak, is a maximum close to the antiferromagnetic transition temperature, not the orthorhombic phase transition, meaning that apparently we have a separation between what we call the nematic, electronic nematic phase transition and the structural phase transition, at least for these two compounds that we have studied. That's not a, you know, that's a surprising result that we want to understand better. So thank you very much.
Thank you, Eduardo. Questions, comments, criticisms? In the previous slide, you have an additional peak at 120 Kelvin. Where it's coming from? That in gray. This.
Okay, sorry. Okay, so these are data from Galea et al. for the undoped system. These extra peaks are phonons.
No, the one in the middle that is not in the higher temperature. Yeah, that one.
Yeah. So this is a phonon that's not allowed for the tetragonal phase, and in the orthorhombic phase it becomes Raman allowed in this geometry of B2G polarization. So that's a phonon that should not be there in the tetragonal phase, but by symmetry it's allowed to be there in the orthorhombic phase.
Since you are interested in separating these two effects, why not pick a material like, say, sodium 111? They differ by a lot, right?
Why not pick another material?
Yeah,
sure.
Sodium 111, they differ by more than just 10 Kelvin, a lot, right?
Yeah.
Sodium 111. Or you can go to lithium 111 or iron cyanide when the magnetic order disappears. Then you can really see what's going on. Because according to what you concluded, if we mentally extrapolate what you have seen to sodium 111, you expect that there will be a very large temperature range in which the magnetic fluctuations keep increasing, right? Which I will find out very surprising. When it's too close, things are mixed together, right? But if you can really separate them from the sample, I think that will be very useful.
The iron selenium, which is the 1-1, you have just the structural phase transition. You don't have the long-range magnetic order, and still have this the Raman nematic fluctuations. They do peak at the orthorhombic phase transition. So
right, so that doesn't help.
Different.
Yeah.
So the sodium system. Yeah. The answer to your question is that because you don't have the samples. I mean, we had the samples, the 1 to 2 samples grown by our Pascual Pagliuso team in our group, and the 1111 sample was given to us by the Ames laboratory group, and we didn't have this sodium material, at least in the first step. But that's an interesting suggestion. We certainly
right, because I'm a little bit worried about your interpretation, because from a very concrete theoretical consideration, this particular magnetic order must come with the Z2 symmetry breaking, right? So it must have some kind of fluctuation right above the critical region. So it's not too surprising that there is an onset. But of course the question is whether that onset is riding on top of something else. And when they are too close, it's very hard to separate them apart, right? My guess is that if you can really go to sodium 111 and separate these two temperature scale, you will see that there is an onset. Then right above magnetic transition, there is one more onset. These are actually two onsets, which make more sense.
Right.
Because there is the system has more than the spin degree freedom, right? This is why you want to treat nematicity as a separate order parameter, because there is this orbital freedom.
Yes.
Right? And actually, we were one of the first to point out this is a ferro orbital order, which is why you can see with Raman, momentum equal to 0 limit, right?
Right.
So it makes sense that there is an onset. It's not too surprising, I think. What's really important to see whether these two onsets are separable. At the moment, it seems that they are too close.
Yeah, what I try to point out is that most groups understand that the nematic phase transition temperature is defined as the orthorhombic phase transition. So the nematic fluctuation should have a peak at the nematic phase transition.
No, hold on. That's the phase changing temperature. So that's the temperature when the symmetry is broken. So right above it, of course, you expect critical behavior, right? You expect some kind of onset.
Yeah.
Nobody says that below which you cannot have another onset.
Right, but
Right.
we didn't see the onset at the orthorhombic phase. We just saw one onset. You see here.
No, but I'm saying that
you don't see that in the height. You don't see any anomaly or any visible anomaly at like 150 something, which is the orthorhombic.
right, but they're too close.
They're not too close. I mean, the reason why we started studying these materials is exactly because the other materials that have been studied before, where it's the lightly doped materials, the difference was 1 Kelvin or less, and that was too close. And then we wanted to say, okay, let's try a material where the separation is like 20 Kelvin, which is, maybe not too close anymore.
So
but you have a point. I mean, you may
make it really
separate big,
right?
different, more the two transitions to see where the behavior starts to change. So yeah, thank you very much.
Could you just remind me, in the antiferromagnetic phase, the spins lie in the plane or perpendicular to the plane?
It lies in the plane.
They lie in the plane.
They lies in the direction of the antiferromagnetic. Let's see. Here.
Oh, I see.
So
okay.
they lie in the antiferromagnetic direction and perpendicular to the.
Okay.
To the
So there's choices to make. Okay, both in the plane and okay.
Mm-hmm.
And so they're locked to the stripe.
Yes.
They're locked to the momentum for the stripe. Apparently.
Yes.
In other words, the doubling direction is parallel to the.
Yes, right. I mean, in principle, it is believed that the magnetic phase transition should be, joined with the electronic phase transition and the structure phase transition. But then we start seeing that they may be different. These two transition temperatures, the orthorhombic phase transition and the nematic phase transition, may be in a different temperature as the magnetic ordering temperature. But they are clearly connected. Somehow they are connected, but not by the same transition temperature necessarily.
Okay. Yeah.
Okay.
Yeah, sorry, I have a question about the clarification about your result. I'm a theorist, I'm not expert of the field. To me, the issue was whether the transition, the nematic transition, was driven by charge or by magnetic order. Your results support magnetic order, differently from other results that were saying it was charge driven. Is this the final point of your talk? And if it's this, may this depend on the material? I mean, so material, this transition might be more driven by charge and the other by magnetic order, and that's the reason why you see different, the peak and different temperatures transition.
Well, I'm not sure. That's a point that we not make. I mean, I'm not sure if our results mean that we are favoring the magnetic mechanism for the as the driver feature for this set of transitions. We saw that the nematic fluctuations has a maximum at a temperature which is slightly higher than the magnetic ordering temperature, but doesn't match the orthorhombic phase transition temperature either. So apparently,
right, but you didn't reach the magnetic transition, right? The nematic transition. Nematic transition is preempted by the setup of the magnetic order, because otherwise you will have a divergence. You will not have a maximum. But you don't manage to arrive. From a mean field point of view, there will be a critical temperature which is lower than everybody, but you never arrive to reach it. And then if it is magnetically driven, you will see the maximum at T magnetical. And if it is charge order and driven, is T maximum at T charge order. That is what I will say. Then I said I'm not an expert. I'm just asking if it is this what you see from the data.
You may be right, but that's a point that we didn't really clearly can make right now. I mean, we have to think more about it.
Further questions?
There's one here.
It's just a minor point. So I think what you're saying is that based on these results, one cannot conclude that the electronic mechanism is actually driving the structural transition, right? Because then they would have to occur together.
Yes.
Right. So that means, at least in this compound, the structural transition is maybe driven by the structural transition itself and not by the electronic mechanism in the first place. Is this a correct interpretation?
Yeah, well, the fact that the transition temperatures are different doesn't mean that they are not driven by something else. I mean, what we think that might be happening is that we have like these nematic fluctuations that starts growing and getting slower, and then it carries the structural fluctuations together with the nematic fluctuations, but the structural fluctuations are really heavy. I mean, they connected to each other by strain, and then they don't want to keep fluctuating. So when they get slow enough, they trigger a structural phase transition that does not necessarily match the electronic phase transition. That's what I think.
The structural transition is first order, is that correct? Because I saw coexistence in your
that's
X-ray data. It seemed that you had.
Well, that's mostly disorder, right?
So what do you think it is? Is it first order? I mean, the mechanism you just described would lead to a
the
first
magnetism.
order.
I mean, the specific heat doesn't show any signature of a first order transition.
I see. Okay.
But that doesn't mean that it's not first order because you have disorder. You have the doping can fluctuate a little bit, and that kind of smears down a possible first order transition. We just can't state it's a first order. It could be, but in the presence of disorder, doping disorder, it's hard to make a definite statement.
Fluctuation above the transition and first order at the same time, right? If you think those fluctuations are important, telling you something important, then you must have in mind some sort of a second order or higher, right? If it's really first order, then you don't care about those fluctuations. Okay.
Okay, thank you.
Further comments? No. Okay, let's thank Eduardo again.
Thank
We
you very
resume
much.
at 11:10. We have refreshments outside.